Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Let's continue with more hands-on sessions on kinetics. Okay. In this class, we will see moving phase boundary problems. We'll start with an example. I'll give the details of it and then how to set up and run in the software. We discussed about the fundamentals of moving phase boundary problems in last class. It is when we want to simulate phase transformations, we will have a boundary between couple of phases. Then we will have to track how this interface, the boundary between the two phases, moves with respect to time. And that's going to tell us about the kinetics of the phase transformation. Okay. The example that we are going to consider is ferrite forming and growing at the expense of austenite in a plain carbon steel. So there is already a phase in the steel, that's austenite, and it will be taken to a set of conditions where ferrite should form according to thermodynamics, and then how it will nucleate and grow, how much time it will take for it to reach the equilibrium content. That's what we are going to track. Okay, so we saw this example of local equilibrium in last class. Here we have this steel material and the percentage of carbon is indicated here. This is 0.15, that's the overall composition throughout the material. If the material comes from a high temperature, let's say this is the composition, overall composition, we keep it at a very high temperature, so it is completely austenite, and then from there we are going to bring it down to 800, and that's where we can put a tie line and talk about if at all ferrite forms, ferrite should have this particular composition, and if gamma touches that ferrite that has nucleated, it should have this composition, whereas the composition of the material at large is going to remain here because it's not going to immediately convert to these equilibrium compositions. Okay, when the nuclei forms, we will have this kind of compositions at the interfaces as indicated by the tie line. Very low carbon, somewhere near 0.02, and very high carbon, somewhere near 0.42. Then this is what it is, somewhere near 0.42, and this is less than 0.02 or so. And this is how the initial profile will start as the nucleation starts, and largely the material will remain with the original composition 0.15, and as diffusion occurs, as the interface moves, we will see that more and more carbon from this region, this blue will grow at the expense of orange. So from the blue region, more carbon will be rejected into this orange region. So that's how the diffusion takes place, and the composition here for the carbon will increase and reach the near 0.42 or so, that level of composition. Okay, so in this regard, how do we track, how do we conclude the simulation is over? Position of interface we are going to track. If it is going to move from here to here, let's say it grows up to some region, and beyond that the ferrite cannot grow, because that's how the lever rule tells you. It says this is how much the ferrite can come. Beyond that, with respect to time, position of interface will be constant, and that's how we will track it. If you put position of interface against time, we will see that it keeps on changing, interface keeps on moving with respect to time, and beyond certain time it's going to be constant, the interface doesn't move. This is where the equilibration is achieved. So we can track this time, this is the time for equilibration. Okay, so this is the setup. 0.15% carbon and iron and carbon, these are the two elements that are going to be there in the materials. We have to set it up, and then we have to simulate growth of ferrite. So we can keep ferrite as a small nuclei ourselves and then see how it grows. We can also do one more exercise where ferrite is allowed to nucleate rather than we putting the nuclei ourselves. Okay, we will see that. So two phases are there, austenite and ferrite. Both phases are homogeneous. Homogeneous in the sense initial compositions are uniform in both of them. So this small nuclei of ferrite has less than 0.02 uniform. Here this is the original 0.15 composition, that is uniform. Okay. Then initial austenite thickness is going to be 2 mm. We are going to keep 2 mm, and ferrite thickness is 1 nanometer. So barely there is any ferrite, that's just a nuclei. Therefore we can keep the rest of the material to have 0.15 composition throughout. And temperature is going to be 1073, 800 degrees Celsius. So we are going to simulate and figure out what is the time to reach equilibrium. Okay, let's do that. Now in the software, we are going to click on diffusion demo. Okay. Then in the package here, we are going to choose FEdemo, MFEdemo, both the databases. So both of them appear here. Then click FE first and Carbon second. Okay. So we have selected the two elements. You can see here. Okay. FE is dependent, Carbon is independent. Alright. You can go to diffusion calculator. You can select the composition in mass percent. The phase diagram I showed you is in mass percent. And length unit, since we want ferrite to be about a nanometer size and austenite to be 2 millimeter size, we will choose a unit which is in between these two things, that is micrometer. Okay. Select micrometer, geometry, let it be planar. Then in this region we can select two regions. One region would be the ferrite, the left one is going to be ferrite and the right one is going to be austenite. Let's see how to do that. So here this region is already there, or there is only one region here. We can click this plus mark so that two regions form. So here region 1, region 2 appear here. So you can click this region 1. Okay. So this in region 1 we can enter the phase name. Here let's enter ferrite. So you can see here the name changed automatically. The moment we enter some width for it, you will see some kind of a diagram appearing here. Let's say 0.002. Okay, so 2 nanometers. This is going to be the thickness of ferrite. So you can see already ferrite appearing here. We don't want in such a small width of a region, we don't want 50 points to be calculated. Let us keep it 10. 10 points are enough and let them be linearly spaced like this. Then let's select the phase also. Let it be BCCA2, that is the ferrite crystal structure, and the dependent component in the composition profile is going to be iron. So to enter the composition here, carbon content, we can check what is the composition of carbon, that is the equilibrium composition of carbon in ferrite phase. Okay, so let us check that at 800 what is the composition. In fact, we can enter any value less than 0.02, it will take care, but let me just tell you how to do that. So here I am going to right click, system definer, create new successor, equilibrium calculator. Okay, and after this equilibrium calculator, create new successor, table renderer. Okay, these two things I create here. In equilibrium calculator, I am going to set the temperature 1073, 073. Okay, and the carbon content is going to be 0.15, that is our overall composition. We want to check what is the individual phase composition for BCC and FCC. So let us check 0.15 here, and single equilibrium is fine. Just perform tree. Okay, so now plot renderer is here. You can see in mass fraction it is given here 0.0015. So that double zeros are added because this has converted the mass percent that we entered to mass fraction. Okay, so here BCCA2 you can see mass fraction which is 0.00012. So what we have to enter is in mass percentage. So we can enter without two zeros here 0.012. That's going to be the composition for carbon in BCC. Okay, let's enter that. Go to diffusion calculator here and enter carbon being linear, going from 0.012 to 0.012. It's a flat profile. Okay, carbon is uniform throughout. That is how ferrite has nucleated. Right. Now go to region 2 here. Click on region 2, and here region 2's name we can change it to austenite, and width is going to be 2 millimeter, so that therefore we can enter 2000 nanometer. Okay. So here you can see austenite phase has appeared here. If you just hover your mouse there, you can see austenite, that is 2000 microns. Okay, that is 2 millimeter, and obviously the ferrite that we have entered has shrunk. It is in fact not visible compared to this, For the sake of understanding, a small red box is put here. That is the ferrite phase, which is just 2 nanometers. Okay, 0.002 micrometers. Okay, so these two regions are there. Now in ferrite we have set a flat composition profile, and points of calculation also are linearly spaced. That's how we set up, and only 10 points of calculation we have set up. But in austenite phase, if we keep these 50 points, that's all right. But if the points are linearly spaced, it's a problem, because we know what happens to the composition profile. The austenite goes to the equilibrium composition near the interface to ferrite, and from there it drops down to 0.15, and with respect to time, that 0.15 will be slowly lifted up to the equilibrium composition. But near the interface, there is a drastic change in composition profile. So more calculation points should be accumulated there. So how to do that is by changing this linear, changing this linear to geometric, and this ratio we can increase to 1.05. You can see as I increase the ratio here, more points get accumulated here. Okay. This is the setup we want. Okay. Then phase we can select to be FCC, that is austenite phase. Okay, FCC. And the composition, what do we need to enter? Composition we can enter 0.15, because barely there is any ferrite found here. Okay, so we can say composition is uniform throughout, 0.15 throughout uniformly. This is our initial profile for austenite. Okay, right. We don't need to do anything else. The boundary conditions, we don't need to bother about them right now. And the temperature, thermal profile we can enter. This is going to be 1073 Kelvin, 1073 Kelvin, and seconds we can change to hours for simulation time, and do it for, let's say, 30 hours. Okay. And then we can simply perform tree. In the plot renderer we can make changes if we want. So click perform tree now. Okay. Then expand this and click on plot renderer here. Okay, you can see mass percentage of carbon against distance has come, and it is still, the concentration profile is like this. It has not become a uniform composition in this side. You can sense this is the thickness of ferrite, which is having very less carbon, 0.012 up to this, and then it starts jumping to this value. So it jumps to a high value and then it gradually comes down. So this is 0.15, the overall composition that we had. So still things are not in equilibrium. If it has achieved equilibrium, the ferrite will have, the austenite side will have some same constant composition throughout. But he said we will track the position of interface, not the concentration profile. Okay, let's do that. Let's see how to do that. Okay. This plot type, you first change it from simple mode to advanced mode so that you get more options. Then x-axis, we want time. Okay, so keep time there, not in seconds, let's keep it in hours. Alright, y-axis is now composition of carbon, we will change it to position of interface. Okay, and instead of meter, let us keep micrometer, and the interface is called ferrite austenite interface, because we have given this name ferrite and austenite for two regions. Okay, so those are the options we are giving. Okay, click perform, and come here and see whether position of interface is constant with respect to time or not. No, up to 30 hours it keeps moving, it has still not become flat. Okay, so we need to increase the time. So let's go to diffusion calculator again, change the simulation time from 30 to 300, then click continue. Okay, go to plot renderer and see here, you can see the setup is already there. Up to 300 we are seeing already in the x-axis. This blue line was up to 30 hours, then this red line comes. Okay, and you can see the red line goes and becomes flat. Almost after some 270 or so it is definitely flat. So that is when we can conclude that the position of interface has stopped moving, and this is the kind of time took it, and this is the kind of time it took to complete the to come to the equilibrium stage. Okay, right. Okay, now in this calculation that we have done in the diffusion calculator, we have set up these two regions ourselves, ferrite and austenite. Instead, we can also allow ferrite to nucleate on its own. We just have to impose one show left interface boundary condition, allow the ferrite phase to form. Okay, let me show how to do that. So in the my project thing, I'm going to click on diffusion demo so that one more project appears here itself. Okay. System definer, you can see the system definer to diffusion calculator 2. In system definer, I'm again going to select package, FE demo, MFE demo, click FE first and carbon second, job done here. Then go to diffusion calculator 2 and here I'm going to change this unit to micrometer, exactly the same things that we have done there. And region, I'm going to click only one region, austenite. I'm going to select only austenite. So now you see austenite, and for this austenite I can set the width that we wanted, 2000 micrometers, and 50 points geometrically arranged in 1.05 ratio so that they are accumulated in the left side. And phase also, let me select FCC and select the composition profile from 0.15 carbon to 0.15 carbon. So carbon flat profile is there. My FCC is now set up austenite side. To the left of it, I want ferrite to nucleate. Okay. So show interface boundary, allow phase to form, none is currently there. Change it to BCC-A2. Okay. And driving force is 1 e power minus 5. So 1 e power minus 5 is a small positive number. Okay. So if there is a small positive driving force for BCC to form, it should form. That's what we are imposing by choosing this option. Okay, and we know at this temperature, if a thermodynamic calculation is done, we know that ferrite will be an equilibrium phase, BCC will be an equilibrium phase. Okay, therefore, it will have a positive driving force, so that it will automatically nucleate and grow. Okay, so that's the meaning of giving this option here. Okay, so since we are just saying that allow phase to form BCC when there is a driving force, it will calculate what should be the composition of BCC. Whatever composition is having the positive driving force, whichever has the highest driving force, will nucleate. That BCC will start becoming a nuclei and start growing. So we don't need to give anything. It will automatically create a region on its own, the ferrite region on its own. It will not call it ferrite region because we have given the name in the previous exercise. In this exercise, it will call it on its own RBCC, region BCC, some kind of a name it will give, and it will calculate. Okay, so let's select the temperature also, 1073 and 300 hours. Okay, then click perform tree. Okay, now we can go to the plot renderer and change to advanced mode, time in x-axis in hours, and position of interface in y-axis in micrometers. And you can see interface RBCC-A2. This is the region generated by the software. Bar austenite, this is the phase that we have given. Okay, so two regions are there, the interface between them will be tracked. Click on perform. Okay, you can see here, since we have run the 300 directly, 300 hours, you can see the graph that we got is here, similar to what we got in plot renderer 1. Okay, same graph. This is plot renderer 1 and this is plot renderer 2. Okay. So this is how you can allow certain phase to form and grow. If there is enough driving force, it will nucleate and grow. Okay. Right. Okay, now you have seen how to do a moving phase boundary problem. Thank you. I hope the lecture is useful. See you in the next class.